All right, hey there, everybody. This is Mr. Wilson again, coming back to you, of course, with the teaching from the Nimitz logo here. And, here I am. Welcome back. We are going to be going over understanding Ohm's law. It's a little bit more about electricity. We're going to be moving forward from this as well. So, continue on from what we learned last week, you're going to see how we're going to do and see what's going on in circuits. All right, why do charges flow? Just like why do things fall? Both happen because of a force. In each case, things falling or charges flowing, there are two different kinds of forces. One is gravity, the other is electricity. So this is the equation for gravity. So this is our universal law of gravitation. It says that the force of gravity is equal to that big capital G, which is the gravitational constant, the mass 1 times the mass 2 divided by radius squared. For electricity, we have this equation. It is the force of electricity is equal to constant K times charge of object 1, which is Q1, Q2, charge of object 2, divided by the radius squared. So in each case, they're both the radiuses are equal to how far the objects are apart. Very similar equations, as you can see. In the gravitational equation, we're talking about mass. In the electricity equation, we're talking about charge. So here we have the sun and the earth. They each have a gravitational pull on each other because one is more massive than the other. So you see the sun is larger than the earth in its mass. So technically speaking, the sun will have more gravitational pull than the earth. In the second case, we have a positive and negative. They're going to pull towards each other because we know that opposites attract from the last lesson, and that will give us the answer. This is just representations of what the equations are showing. We would measure that distance in between these two to give the radius. But electric force can also repel. That is the biggest difference between gravity and electricity, is that electrical forces can repel each other. What do we mean by repel? So similar charges are going to push away from each other, or like charges. Why do charges flow? The force always pulls objects from positions of high potential to positions of low potential. Okay, what's high potential versus low potential in gravity? So high potential is very high up, low potential is very low to the ground. If you remember from our potential energy, kinetic energy lessons from before we were out of school, high potential is up, really high, low potential is low. Electricity, the first position has greater potential than the second position. Well, why is that? It's doing the same thing here. Bigger potential difference because there's a larger space between the two of them. So the farther away you are from the ground is gravity, the farther away they are from each other is potential in electricity. So the force pulls objects away from positions of high potential to positions of low potential. So why are we talking about a battery now? How does it have potential energy? So on the positive side, there's high potential. On the negative side, there's low potential for electrons to flow because electricity flows from the positive to the negative terminal usually. So it goes from high potential to low potential. So that's what you're seeing here in this problem here. You actually see the battery in the middle. The battery's going to have the electricity flow from the positive to the negative side, high potential to the low potential. Batteries provide potential. Potential what? Potential for electricity to flow. Like an elevator provides gravitational potential. So an elevator goes up or down. It has more or less potential depending on where it's at. It converts mechanical energy into gravitational potential energy, pushing against gravity. So what's that mechanical energy? That's that energy applied in the gears or pulley system, typically with a counterweight, and using electricity to move an elevator up or down is what allows it to change its potential energy. In the case of the battery, it converts chemical energy into electrical potential energy, causing a flow of charges against the electric field within the battery. So that's why you see this battery says alkaline on it. You can see lithium batteries as well. There's nickel cadmium batteries. There's lots of different kinds of batteries you can see. Even your phone has batteries, and they're all very different batteries each time. Each one has a different amount of potential to it. So since each one has a different amount of potential to it, that means you can have more or less charge in each one of those objects. In this case, you have voltage. The electric potential difference between two positions is called voltage. So you're actually measuring the difference between the potential here and potential there to get a voltage. 1 volt is equal to 1 joule per coulomb. So that's the amount of energy per charge. Higher voltage is equal to more energy difference and a stronger pull on charges. So a larger voltage means there's more potential difference between the high potential and the low potential area, and there's more change in that charge, and it's going to pull it harder, so cause it to move more. So you got a picture of batteries. How many volts are in each of these batteries? Well, each one has a very different size, but they all provide a 1.5 volt of potential difference. Why is that? Surprisingly though, 9-volt batteries provide 9 volts of potential difference. So the difference between these two these four here, the AAA, the C, the D, and the AA, and this one. Well, this one's a 9-volt battery. That's why we call it a 9-volt battery. And the other ones we just label as either A, AAA, AA, AAA, C, or D. If you ever were to open some of these C's or D's, typically they're actually comprised of the smaller batteries. There may be 3 A's in a C or 5 AA's in a D. That's the way it works usually. So what's the difference between them? The D stores more energy, so it lasts longer. Bulbs burn the same brightness. So if you were to if you could make a AA the same length as a D battery, make it fit in there and touch each of the connectors where it would be able to conduct the charge, it would actually give the same brightness. It just wouldn't last as long as the big old D battery. But a 9-volt will actually burn a little differently because it has more voltage. So voltage is Ohm's law, VIR. Here we go. Voltage measured in volts using a voltmeter. Current is I, measured in amperes or amps using an ammeter. R is resistance, measured in ohms. Or omega, it's the symbol there, using an ohm meter. And some voltmeters are actually a voltmeter, ammeter, and ohm meter. Together, they're called multimeters. So multimeters. So voltmeter, ammeter, ohm meter, you can also find it as a multimeter. So in the other part here, you have I is equal to VR. That's just a different way of writing this equation, because now current is equal to voltage divided by resistance. What is current? So current is the amount of charge flowing per second. So as in representation, you have to say where's the point the current's flowing from. You would take this little cut right here. Every time you take 1 second, and if 1 passes through, it's 1 coulomb per second, which is 1 ampere. But if, say, you take this as your measurement, if you're for 1 second, if 3 of them pass this space, this cutoff point right here in 1 second, then now the charge would be 3, because it's 3 coulombs per second. Current is the rate of flow as charge moves through a circuit. What's a circuit? Talk about that more. We talked about that last time. Just like water, more potential causes more current. So in each case here, still water, not much potential. It's not very moving much. More energy change here because you've got a little bit taller waterfall, a little bit of change because the water's got to go from up here to down there. And then a really tall waterfall, you're going to a lot of energy change, a lot of potential energy to fall, turning into kinetic, so it falls fast, and then hits the water down here. So I is equal to voltage divided by resistance. So current is equal to voltage divided by resistance. Increasing V should increase I because they would be directly related. Resistance opposes the flow of charges. So what is resistance? In this little picture here, you've got a battery that's a pump that would be pumping things upstairs because you can't really make things go upstairs easily. If things going around, that's the potential energy for it to go there. It wants to go down, but this little wheel here is a resistor. It's slowing it down because if you see these are a little bit, they can be closer or farther apart depending on what happens here. There's some spacing changes. That resistor resists the flow, makes sure it's not just going super fast and going faster and faster. Think of it like rocks in the river, slowing the flow. So what does that mean, rocks in the river slowing the flow? So when you look at a river, if it's just a smooth concrete bottom, say you created your own river, it was just smooth concrete, it would flow really quickly because there wouldn't be as much resistance to the flow because it would be able to just go right on top of that smooth top. That's why our pipes are all smooth and not porous or bumpy. Now, if you were to look at a regular river, they flow more slowly because all those rocks are actually causing different changes and causing more surface area because of their unlevel positions. So it actually causes more resistance for the flow of the water, so the water catches on all those little rocks. And then in turn, the rock smooths those rocks out because it moves over them so much. Electrical components like light bulbs have a higher resistance than wires. So why is that? Oh, yeah. So why is it that they have higher resistance than wires? So wires are just conducting the charge. A light bulb, like is a high, we call it a resistor, even though wires have resistance, we call a light bulb a resistor because it uses and causes that electricity to build up so much that it changes the electrical energy into light. And usually it used to be more heat energy to cause where you would actually see that bulb light up. That's why we talk about bulbs in heat amount. So sometimes you say 5,000 Kelvin, 6,000 Kelvin, or 9,000 Kelvin bulb, because each of those are different heat ratings to where that bulb is actually burning at a certain heat amount. Whenever it's doing that, the filament is actually charging up to a certain point to where it actually gives off heat. That's why if you ever touched a hot bulb, because that bulb has been getting so much electricity to it that it actually heats up and causes that electricity to turn into heat and give off light. So learning resistance through straws. So is it easier to blow through air through what? A long straw or a short straw? Many straws or few? A wide straw or narrow? Okay, so a longer straw is harder to blow through than a short one because there's more resistance, because you're putting it through a longer space. Many straws are few. You can't blow through that many straws because you wouldn't be able to put that much air through all of them. A wide straw or narrow. So a very wide straw you can push through really well because there's not very much resistance, but a narrow straw you can't push through as well because you would have to blow for a more continuous, longer period of time to get the same amount of airflow through. Same is true for electricity. There is more current and less resistance in short wires with multiple paths and wide wires. So when we need more electricity to flow, we go with shorter distances. We try to move the source of electricity closer to the item we're trying to give electricity to. Multiple paths. So the more paths you give, the more electricity you can flow. And then wide wires. So you make a bigger wire to cause more electricity to flow through. Just like if you have a phone cord, it's not going to put as much electricity through it as if you have a big extension cord for your air compressor. Necessarily, you're going to do something like that. What is a circuit? Well, circuit we learned about last week. Complete path for charges or electrons to move. The material the charges move through are called conductors. Moving charges carry energy obtained from their source that can be used to do the work. Just like I talked about earlier. We talked about circuit diagrams a little bit last time. So single cell, a battery, connecting wire, or resistors, a squiggle line, switch is the open that goes up, open or close, be either one. An ammeter or a voltmeter will be always marked with a big A or a V like that, the circle. So in each picture here, you've got two different drawings and a schematic. So the drawing gives you a better idea of what the batteries look like. The same picture on the right is the schematic diagram. It just shows you to in the symbols instead of like showing bulbs or batteries. So here's some practice. How much resistance does a light bulb have if a 3-volt power source causes a current of 0.5 amps? And what is the voltage of a battery in the following circuit? 2 questions to answer. Hold on just a second. Daughter's here, making an appearance. So take your time to go through this, and I'll come back to you in just a minute. All right, hopefully you've got your answers in. We're going to go over that now. And the first problem here, we don't use the picture. And the second problem, well, you will use that picture. 3-volt power source causes a current of 0.5 amps. So in that picture, there we go. And then it says, what do we got? So we're using voltage is equal to current times resistance. We're going to rearrange the equation here. So VIR, rearrange it to R is equal to I divided by V. R is equal to 0.5 amp divided by 3 volts. So our R is 6 ohms. Why does 0.5 divided by 3 turn into 6? Because remember, multiplying